grocery store and you see apples and you say, I want to buy some apples, and you look at the apples and you give them $2 a pound or whatever. Or you go into a car lot and you're going to buy a car and you look at the car and you buy the car or whatever. You order an analytical laboratory test, and when you get it back, you get a piece of paper, and the piece of paper has a number on it. You paid $400 for the number. Say, is this worth $400? I mean, what's a good value for your money? And it's a kind of an appropriate question. This is one of those times when government intervention is necessary, or some kind of intervention is necessary. Laboratories, close to without exception, are regulated and certified. The regulations on the laboratory are, every single tiny little corner of it is regulated. And they're certified to meet the qualifications that are necessary to do the work. The agencies are the Food and Drug Administration and the U.S. Department of Agriculture, the FDA and the USDA. Medical laboratories around the country are regulated typically by the State Department of Health. In recent years, Medicare, which is a big spender of money in laboratory services, has become a big source of regulation. Our focus here is on the 8270. The 8270 is regulated by the Environmental Protection Agency. The Environmental Protection Agency sets up a series of gauntlets for the analyst. The gauntlets are, you do step A according to this procedure, then step B, then step C, then step D. At step E, you have to pass this criteria to move forward. Then you do F, then you do G. Step H, you have to pass this criteria. This is very common in analytical chemistry, is that you've got to meet certain specifications along the way in order to report the results. Analysis produces errors. The person that receives the analysis, the person that looks at the results, is aware that there are errors, but is assured that the errors are under control because the laboratory has been certified by whatever the agency is. Let's just do it as an example. We, of course, are looking at the 8270. The 8270 is environmental analysis for semi-volatile hazardous waste. Walgreens is building a store at the corner of Colfax and Wadsworth in Lakewood, Colorado. The consultants, as part of the environmental assessment, say, we want an 8270 done on this site. They pull a sample for the 8270. They do it in specific ways, put in a specific type of container. The first laboratory constraint is that sample has to be extracted in methylene chloride and blown down to an ASV, and it has to be done in 7 days. They're saying the sample's not stable. It's just not. It's not stable. You can't let it sit around. They've got 7 days. In the business, we call this the holding times. The holding time is 7 days. The methylene chloride extraction now is more stable, but it's still not extremely stable. They're saying you have 40 days to analyze the extraction. So the 7 days is the first time limit. 40 days is the second time limit. The first gauntlet in GC Mass spec is the DFT PP criteria, decafluorotriphenylphosphine, I believe it is. Decafluorotriphenylphosphine is a molecule like other molecules, and like other molecules, it fragments in a pretty specific way. The DFT-PP is picked because it has ions throughout the range. The heaviest, the base ion, is 442, which is about as heavy as anything you're going to see in the 8270. The DFT-PP is injected like other injections, and it makes a peak like other peaks. The operator goes to the peak, left clicks on the peak, and then right clicks, and brings up a menu. The menu includes a DFT PP, so you click on the DFT PP, and it generates a table that looks pretty much like this one. There's a spectrum, and it gives a table. It automatically does it. It's complicated, I'm sure, but as an operator, it's just a matter of a mouse function. The sorts of things that the DFT-PP look for are, there's two of them. One of them is, are the masses assigned properly? Are the mass assignments leaking into the neighboring masses? And then the last point is, are the ratios of the heavy compounds to the lighter compounds, are the ratios right? Or is it biasing the heavy compounds more than the light compounds? Things such as, if we look up here, we can see that there's a big mass 69. Is the mass 68 big? Or is it just, there shouldn't be any mass 68 or hardly any, and there shouldn't be any mass 70 or hardly any. If there is any, then that tells the operator that the masses are not getting assigned cleanly. The 198 is a big peak right in the middle of the run, and the 442 is a big peak right in the middle of the run. Are these two at their proper ratios? And my experience as a mass spec operator is that the DFT-PP criteria can be a problem. And sometimes you have to average the scans. The 8270 specifications are very clear. You can average scans, you can subtract a neighboring scan, and you can play with it. I've never seen the DFT-PP not pass. I've struggled with it. It can be a problem, but I've never seen it actually not pass. Part of the prep is a prep blank. The prep blank is a check to make sure that the extraction system is clean and not generating any extra stuff. I don't think I've ever seen a problem with a prep blank. The glassware is cleaned in a furnace, and it's cleaned and dried. And I don't know how you could ever have a contamination unless the methylene chloride itself was extracted. If the prep blank is not clean, the whole extraction, the whole thing is thrown out. You don't say, well, this is too bad. No, you throw the whole thing away and start all over again. I don't think I've ever seen that happen before. The 8270, like every analytical process, involves a calibration step. The initial calibration for the 8270 involves 5 points. There are 20, 50, 80, 120, and 160. A standard, which is 20 of everything, that is 20 of all 70 analytes, is injected and gives 20 response factors, gives 70 response factors according to the 20 standard. The next injection is a 50 standard for all 70 analytes. So you inject a 50 standard, an hour later the run is done and you have a response factor corresponding to the 50. Then you run one for 80, then you run one for 120, and then you run one for 160. So it takes about 6 hours of instrument time, five hours of instrument time, to run the initial calibration. To generate this table is really a function of mouse clicks. You just mouse click and you put the names of the files in the program, turn the program on, and it spews out this table. Let's take a look at this in some detail. We have the names of the analytes going down this way. I like phenol because it's easy to pronounce. Bis-2-chlorohexylethyl ether. 2-fluorophenol is a surrogate. Phenol D6, notice it's a stable isotope, is a surrogate. 1,4-dichlorobenzene is an internal standard. There's a lot of quality control peaks in it. Across the top, we have the 20, 50, 80, 120, 160. So the first injection is this column. An hour later, second injection is this column. Third injection, fourth injection, fifth injection. The average is in this column. And then the statistical treatment under the EPA is pretty simple. They do a standard deviation of the response factors, and then divide the standard deviation by the average to kind of normalize them all, and you get a percent relative percent standard deviation, so that they can be compared one to the other. Let's see. Is there anything? Let's take a specific case and look at this a little bit as a review for how the calibration works. The initial calibration is 70 calibration curves, each of which has 5 points. So let's kind of narrow this down to one analyte. I pick phenol because it's easy to say. And this guy's a benzene ring with an OH. It's somewhat familiar. So we run a 20 standard. The 20 standard has 70 analytes in it. It makes a big chromatogram with lots of stuff in it. Let's only look at the phenol. The phenol at a 20 gives us an area of 28. So the 20 gives us an area about 28, which is, let's put it right here. That point with the origin defines a line, and that line actually could be used for quantitation. We run a 50. The 50 gives us an area of 70. That point, including the origin, defines a line with a slope. That line can be used for quantitation. We run an 80, along with all the other analytes. We get a response, we get an area for the 80 of 116. So the 80 gives us 116. Let's put it maybe about right here. That point with the origin defines a line, and we could actually use that for quantitation. And then there's two more. The 120 gives us a 162. Let's put it about right here. That defines a line, which could be used for quantitation. And then finally, I don't have blue. And then finally, the 160 gives us a 214, which is up here. And this defines a line, which we could use for quantitation. The response factor is the slope of the line. Notice how the slopes are similar. They should be similar. The response factor is the slope of the line. For those of you who are really paying attention, might be thinking that, well, wait a minute. This is an internal standard calibration, and the area is actually the ratio of the area of the target to the area of the corresponding internal standard. Just kind of as a little complication, but we're talking about quality control here. The quality control considerations from the standpoint of the EPA are two parameters. One of them is that they want to see the slope of the line to be above a certain point. Like the slope of the line has to do with like the sensitivity of the instrument generally. If it's a real steep slope, then the instrument is real sensitive. If it's not steep at all, then the instrument is not very sensitive to it. 2,4-dinitrophenol is what they refer to as a poor responder. It doesn't respond very well on the mass spec. It sticks in the injector quicker than just about anything. The Environmental Protection Agency says that if the response factor, if the average response factor, which is this guy, is above 0.050, 0.05, so if it's up above about here, pretty low, then the sensitivity of the instrument is adequate. Analysis produces errors. The second parameter that the Environmental Protection Agency looks at is how close are these slopes. You can see the errors in the slopes. I mean, you really don't even need to look farther than that. You can see the errors in the analysis right in the slopes. They're saying that the errors need to be under control. And again, they look at a particularly weak player in it. And this pentachlorophenol has very erratic behavior. Sometimes it's very erratic. If the instrument is not working perfectly, the first problems are going to be seen in the pentachlorophenol. They want to see this parameter for the pentachlorophenol to be less than 20. So the windows can be pretty big. And if all of these things pass, then the initial calibration passes and you can move forward with analysis. My experience as a veteran mass spec operator is that the initial calibration can be a problem. Sometimes you have to fight with it a little bit. Sometimes you have to fight with it a lot, but it'll just about always pass. So the initial calibration is passed. A very common theme in analytical chemistry is that you run a calibration and then you check the calibration against a control. The control for the 8270 is typically at a 50. The 50 control is not really different than the 50 in the initial calibration. At the beginning of the day, the operator runs the control or checks the DFT PP to make sure it passes, and then runs the control. The Environmental Protection Agency knows where the weak points are. And this is a bit of a simplification, but if the 2,4-dinitrophenol is over 40, and if the pentachlorophenol is between 40 and 60, that's plus or minus 20%, then the concal is considered, the continuing calibration at 50 is considered to pass. There are other things to look at. The retention times from the previous day can't move more than 30 seconds. So it's kind of an important issue because the retention times can wander as the column is cut off, but not more than 30 seconds a day. The internal standard areas have to be between 50 and 200%. So they can go from half of where they were to twice where they were the previous day, and you're good to go. The windows are pretty big. The mass spec is an incredible instrument, but in some ways it's kind of not very stable. And the internal standard areas will jump around. And the EPA is saying they can jump around, but not more than from 50% to 200%. So if all of these things pass, then the continuing calibration is off, and you're pretty much off and running for the day. First thing you run is a method blank. The method blank has to be clean. Then the samples are run. The samples have surrogates, which were added before the extraction. So they're kind of like fake analytes, and they're tracked through the extraction, through the analysis. The surrogates have to be within certain levels for the sample to be reported. If it's not within certain levels, the sample can't be reported. If any quantitations go over 160, then they have to be diluted down. That sample has to be diluted and rerun because the linearity is questionable over 160. And there's good reasons for that. In fact, you actually can see that in this. Table that the response factor goes down as you go up, which is typical of mass spec. It's not very linear at higher levels. We have been studying the 8270. This is like my 8th video on the 8270, and this is the very last one. The 8270 is good because in some ways it's very typical. The scene of running an initial calibration and then at the beginning of every day starting out with a control to see if it fits is very common in analytical chemistry. The 8270 is more complicated than other tests that I know of, but in many ways it's very typical. If you have a mass spec in your lab, go look around in the software and you will find a software package really for the administrative reporting aspects of the 8270. There's a lot of specialized stuff that goes on. The people that make mass specs write software specifically to treat this data because the 8270 is a very common analysis. And that's it. And thank you.